Okay, so now we're going to look at the behavior at zero. So we're going to go away from left and right hand behavior, and we're now going to start talking about at zeros. Now, the definition of zeros is the following. Most of your polynomial functions of odd degree are shown next, and then we're going to look at even. And all these polynomial functions of odd degrees, there is at least one real value of x that makes f of x equal to 0. Okay, well, that makes sense because the left hand behavior goes down, the right hand behavior goes up, and they have to cross the x axis at some point. This is your x intercept. So there has to be at least one. So as we look at these examples here, this is the function 2x cubed plus 8x squared plus 2x minus 12, x to the third power. It factored out. We have 3x binomial factors that turn into zeros or x-intercepts. Now here's the difference. These are two different things. A 0, that's the x that turns the function into a 0 for the y-coordinate. That's the same as an x-intercept at 1, 0. We have a 0 at x equals negative 2. We have an x-intercept at negative 2. We have a 0 at negative 3 for x. We have an x-intercept. They're labeled differently. Now when we get to this one, still x to the third, but now notice that there's only one real 0. It only crosses the x-axis once. However, though, when we factor and solve this, we get 1, 0 that's a real number, which associates to that x-intercept. But now these two zeros, they're complex or imaginary numbers. We cannot graph them on the x-axis, so they do not exist. So there's the difference. It's still a 0. It's just not an x-intercept. Here we have x to the fifth. We have two zeros here. One at negative 2, one at 1. When this is factored, we have binomials that repeat, so we're just going to write them raised to that power. So 0 at x equals 1, x-intercept 1, 0. Solve for x equals negative 2, that's the 0, that's the x-intercept. If we look at even degrees, now it's questionable whether or not we'll cross the x-axis because it's possible that everything stays above. All right, so here's x to the fourth minus 5x squared plus 4. Again, it factors, and we can solve all these for x. So here, because you have x equals 1 and x equals a negative 1, we can write the zeros as x equals both positive, negative 1, and the same thing with the x-intercept. Here we have x equals 2 and x equals negative 2 when we solve it. So again, we can say this is a 0 at positive negative 2, or your x-intercept at positive negative 2 comma 0. My next one here, this one gets really interesting. It's factored. X equals negative 2 is a 0. Negative 2, 0 is my x-intercept. I have x equals a negative 1, and I have x equals a positive 1. But notice I didn't write it like this. And that's because both binomials are raised to a different power. That's important to understand because that's going to take us to our next concept here. So again, looking at this one really closely, it's a 6th degree, but it has 3 distinct real zeros. But each x-intercept acts differently. That's because of the multiplicity of the 0, which means how many times did that x-intercept or that 0 repeat itself. So here, because x plus 2 only occurred once, you have a straight line going through this graph. That's what we call a multiplicity of 1. You don't have to declare it, but it's raised to the first power. So at negative 2, right here by that x-intercept, it has to look like a linear line going through that x-intercept. For x equals negative 1, or the x-intercept negative 1, 0, you have a multiplicity of 2. So that has to look like an x squared. So this has to look like a parabola. There it is. There's my little parabola at that x-intercept. This is what we call a touch and go. It comes down and touches the x-axis and turns and goes back up. And our last one has a multiplicity of 3 because of that power of 3 there. So now at this 1, it has to look like a cubic curve when it crosses the x-axis. All right, there's the difference there. So if we go back to the last picture in the odd degrees, let's jump back here real quick, because again, here at x plus, or excuse me, at the x minus 1 squared, that's a multiplicity of 2. There's that parabola shape. X plus 2 to the third power. Yep, multiplicity of 3. There's my cubic looking graph right there. So we're going to be graphing polynomial functions. We're going to be making rough sketches. So we want to make sure that we appropriately draw the graph's curve at these x-intercepts. So if it does have a multiplicity of 3, I don't want it to make it look like a straight line going through. It's got to look like a cubic curve. So multiplicity of 1, a straight shot through, either going uphill or downhill. One x-intercept. If you have a multiplicity of 2, it's a touch and go going up or touch and go going down. If we have a multiplicity greater than 1 that looks like a 3 or a 5, it's going to come in, flatten out for a little bit, and take back off. These are what I call my cubic curves right here. Author says it wiggles. I don't see the wiggle there. It looks more like a shimmy.